Okay, so far we were discussing the case where the bounded region is above the x-axis. Now, what if the region has some pieces which are below the x-axis? In that case, the total area of the bounded region is equal to the area of the region above the x-axis minus the area of the region below the x-axis. And that total area, we call it the net area. And sorry, and here is the definition. Let R be the region between a continuous function fx and the x-axis, between 2 points x equals a and x equals b. The net area of R is the sum of the areas that lie above x-axis minus the sum of the areas below the x-axis. The net area can be positive, negative, or zero. And this depends on the size of the pieces above the x-axis and the pieces below the x-axis. If the piece above the x-axis is greater than the piece that is below the x-axis, the net area will be positive. If it's opposite, then the net area will be negative. If the piece above the x-axis and below the x-axis they are the same, then the net area will be equal to zero. Now, why this is true? Because we know when we are constructing the rectangles, we said the height of a rectangle is given by the function value of a point in the subinterval. Suppose right now we have a rectangle looks like this. Because the function value is negative, because this piece of a graph is below the x-axis, so the function value is negative numbers. And the width is always positive, no matter how short it is. It's a positive number. So that's why the area of this rectangle is a negative. Therefore, the sum of rectangles like this will still be negative. That's why the area of this region will be negative. Okay, so the total area of this gonna be the positive area of this region and plus the negative area of this region. That's why we can see as it's the area of this minus the area of this. Okay, let's say, for example, if the total area of this region is positive 5, and the total area of this region is negative 2. So the total area of this gonna be 5 minus 2. Okay. So that's why in the definition, it's the sum of areas that lies above x-axis minus the sum of areas below the x-axis. That gives us the net area. Okay, now let's take a look at this one. Here we are given the graph of a function fx. So we want to determine is the net area positive, negative, or zero. So if we compare the area of the regions above the x-axis with the area of the region below the x-axis, we can see the green part, the green pieces, the sum of them are way smaller than the blue piece. Therefore, the total the net area here is negative. Okay, so the answer is negative. Okay. Now, in the previous video, we said that if a function is integrable, if a function is integrable, then the limit of the Riemann sum exists, and the limit of the Riemann sum will give us the exact area of a bounded region. Now here is the same thing. If the graph of a function is continuous, then the function is integrable. Then the limit of the Riemann sum will exist, and the bounded region, we can use this notation. We can use this definite integral to represent. So like here, since the net area is positive, therefore this definite integral gonna be positive, and this definite integral is negative. And for this one, the definite integral gonna be 0. Okay, so as long as the function is integrable, the limit of the Riemann sum exists, right? And when we construct the Riemann sum, we set the width of the rectangle and the height of the rectangle can be determined randomly, right? Now, in order to make our calculation to be convenient, so we want to choose the easiest way to construct the rectangle. So what is the easiest way? The easiest way is we can let the width of each rectangle to be the same. And when we determine the height of each rectangle, we just follow one pattern. So that pattern is we can use either left endpoint or right endpoint to determine the height. Therefore, if the function is continuous, if the function satisfies the condition, if function is integrable, then in practice, we just use either the right Riemann sums or left Riemann sums to calculate a definite integral. So here the xk star is the left, so is the right endpoint on each subinterval, and all the delta xk will not be the same. And after we find out what this summation is, and we take the limit, we let delta x approaches 0. Now, when delta x approaches 0, this is the same as we let n approaches infinity, right? Because the more the rectangle we have, the short the length of subinterval is. So if when the length of the subinterval approaches 0, it's the same thing as we have the number of rectangles approaches infinity. Okay. So in practice, when we are evaluating a definite integral, if the function is integrable, we use the limit of the right Riemann sum to do that. Okay, let me use this example to illustrate this method. Okay. here we want to find the value of this definite integral by using the definition of definite integral with right Riemann sums. So first, to do this, we need to figure out how to write this summation. Okay, and by looking at this integral, the integral from 0 to 3 x squared plus 2 dx. If we compare this with this notation, we can see that the 0 is the a, which we call this as the lower limit or the lower bound of the integral, and the b, we call it upper limit or upper bound. So the upper bound is 3. Okay, and the function fx is x squared plus 2. Okay, so once we figure out these three things, then we can first figure out how to write delta x, because we here the width, the delta x is the width of the rectangle, which in the previous lecture we said it's given by the formula b minus a over m. Since we know what are b and a, so that will be 3 minus 0 over m. Okay. So delta x is 3 over n. Now, once we know how to write delta x, we can know how to write this piece, a plus k delta x. A plus k delta x is 0 plus k times 3 over n. So it's 3k over n. Now, in this term, remember this term a plus k delta x, you should have a variable k and a variable m. If you don't have these two things, that means your answer is not right. So you wanna check. Okay, and the next thing is to decide to figure out how to write f of a plus k times delta x. Since a plus k delta x we figure out is 3k over m. Therefore, to find what is f of so here is like to find how to write f of 3k over m. So this is like a practice we had in pre-calculus. So this is like we wanna evaluate the function when x is 3k over m. The function is x squared plus 2. Therefore, when x is 3k over n, the function is 3k over m squared plus 2. All right, so now after we determine these three things, we can write this summation. So the summation k from 1 to n f of a plus k delta x times delta x will be the summation k from 1 to n. Let's first write this piece, which is 3k over n squared plus 2. Okay, And don't forget, there is another delta x and times 3 over n. Okay. Now, next thing we need to do is to simplify this summation, so we can write it into an expression that only contains n, and then we take the limit of that expression, and then we can find a number. If the limit exists, then we can find a number. That number will be the answer to this will be the answer of this definite integral. So when we are when we are doing this, we are gonna use the thing we learned from the sigma notation, the results from the sigma notations, especially the formulas and the property of the sigma notation. Okay. So let me go back to here. Now, since each term in the summation contains 3 over m, right? Because if we write the first few terms, the first term is when k equals 1, so that is 3 times 1 over m squared plus 2 times 3 over n, and plus the second term is when k equals 2, 3 times 2 over n squared plus 2 times 3 over n. So you can see only these numbers are changing, right? Therefore, 3 over n is a common factor. Since it is a common factor, we can first fact out 3 over n. So to write this as 3 over n times this summation. Okay, now next, since this is a summation of this term 3k over n squared plus 2, if we use the property, the second property of the sigma notation, the summation of a sum of two terms, we can write it as a sum of two summations. So we can continue to simplify our answer into the sigma of 3k over n squared plus the sigma of 2. Now, the summation of 2, this is like we have 2 plus 2 plus 2 plus 2 for n times. So the result is 2 times n. For the first summation, if we square 3k over n, we can have 9k squared over n squared. And this summation is like 9 times 1 squared over n squared plus 9 times 2 squared over n squared plus 9 times 3 squared over n squared plus 9 times 4 squared over n squared. So we can see each term has a factor 9 over n squared. So therefore we can fact out that okay. Now once we get here, the summation of k square, we can use this formula to find what it is. So the summation of k square will k from 1 to n, that equals n times n plus 1 times 2n plus 1 over 6. So this equals n times n plus 1 times 2n plus 1 over 6 plus 2n. Okay, now you can see in our result, we don't have any k, right? Everything is written in terms of n. So the next thing we're gonna do is to simplify this expression, and then we take the limit as n approaches 0. So that means right now we have infinitely many rectangles. So to simplify this, okay, we can first cancel this n, so we can have and 9 and 6, they have a common factor 3. So we have 3 times n plus 1, 2n plus 1 over 2n plus 2n times 3 over n. So then we multiply the 3 over n into this. So we have 9 times n plus 1 times 2n plus 1 over 2n squared and plus 3 over n times 2n, that is 6. Okay. And so the summation of f of a plus k delta x times delta x equals this. Now we take the limit. The limit of this summation is equal to the limit as n approaching infinity of 9 times n plus 1 times 2n plus 1 over 2n squared plus 6. Using the property of a limit, we can split this into the sum of the limit 9 over 2 times n plus 1 times 2n plus 1 over 2n squared and plus the limit of 6. Alright. So the first, the 9 over 2, since this is a constant, we can write it outside the limit. Okay. For the first limit, this limit has the form infinity over infinity. because the numerator, if we multiply the numerator out, n plus 1 times 2n plus 1, this is 2n squared plus n plus 2n plus 1, so that is 2n squared plus 3n plus 1. The numerator we can rewrite as 2n squared plus 3n plus 1. The leading term of numerator and denominator are n squared, and the leading, since the degree of the leading term are the same, then we set the limit equals the ratio of the leading coefficient, which is 2/2. So the limit of the first term is since we fact out 9/2, so the leading coefficient is 1. Okay. So the ratio of the leading coefficient is 2 to 1. So this limit equals 2. And the second limit is a limit of a constant, so that equals 6. So the answer is 9/2 times 2 plus 6, which is 9 plus 6, which equals 15. So the answer of this definite integral equals 15. Okay, 15.